Hello everyone. As you know that I've been working on this robot Jumpy for quite some time. So the hardware is almost complete. I have made the whole structure and I've described it here on my YouTube channel. These are the legs and this is a PCB design, and I had connected all the servos and PCB design, PCB everything, and programmed the basic motions like standing up and waving the hand and everything. So it's quite some time since I made the last video because I was working on the programming part. And the programming part, I had to describe everything the robot has, like the all the lengths, all the servo configuration, all the angles and everything. So that took some time, and I wanted to a robot move like the actual the dogs or the animals would, you know. So to start with the leg motion, I just follow this diagram. I'll be updating this whole structure because I use the PLA filament for the legs, and it happens to be like I didn't know, but it's a very weak plastic form of plastic. So after some time, there are cracks everywhere on the legs. So you can see I have put some glue on the legs. So I think for a proper gait motion, I'll be replacing all these plastic parts with the metallic parts to remove all the flags and everything. So this is the leg. So for now, I'm focusing on one leg motion. So for the one leg motion, I have this chassis. This is the servo. This is the hip servo, and this is the femur. Like this is the femur, the femur joint, and this is a knee joint, or this, and this is the shank. So I can I have this another diagram. So normally when the robot is standing, like the default values are here. This is 45 degrees, this is 135 degrees, whichever I want to take I can take. But like I've made a note of everything. This femur length is 55 millimeter. Sorry for the low quality of the picture, but this is the hip, like a spacing here, spacer, bracket, whatever you say, is 35 mm. This is the shank is also 55 mm, but the length, the angle that it makes with the femur joint, with the femur here, is 60 degrees from this side and 120 degrees from this side. So once I have all these dimensions, I also wanted to share the convention, because in order to program the kinematics and the inverse kinematics, you need to take a certain assumption for your axis, which is your fixed reference and what are your servo references and everything. So I'm taking this yeah, so I've taken this right hand rule, and where the index finger is the x-axis, which is through the front part of the chassis. The y is where my robot will be heading, and z is the perpendicular to xy plane. So on the opposite sides, we have the negative of all these three axes. So if my hip servo is like this, the z-axis would be pointing down. That would be negative z-axis to the ground, and the servo, by its length, it will be aligned to the chassis, front part of the chassis. And if I look at the knob, and if an arrow comes out of this knob towards me, out of the screen, it will be the y-axis. So it will be essentially following this right hand rule. So okay, and here is the axis. This is x-axis, this is the y, this is the z, as we do in the normal convention of the axis that we take. And this is the y-axis. I have also taken the certain, I think it's normal to take the clockwise rotation is a negative rotation, and the anti-clockwise rotation is a positive rotation. This is another diagram that shows how these servos are considered. And okay, so this is a chassis. The chassis is the fixed reference, and the way the reference it follows is here. This is the Y, the front part. This is the forward direction, and the upward direction is a positive. So it's a negative here, but like upward is positive, downward is negative, and backwards is the negative y-axis. And yeah, if I look inside the screen, if our arrow goes from the screen to the back side, it will be your positive x-axis. Okay, once these conventions are set and all the lengths and everything are known, we'll be proceeding to this 2D simulation. So the good news is that I've made this GitHub page where this is the Jumpy, my project here, and this Jumpy project will be containing everything regarding the simulation and all the motions that we are playing. So my goal is to lead you from the scratch and in detail put all the documents in detail, like how a mature, how a newbie would be starting the and this four-legged quadruped robot. So first of all, we'll be starting with the one-leg motion. So for the one-leg motion, I have this 2D code in here where I've defined everything, like the length 1, length 2. This everything is modifiable in here, and the step length, the step height, num points. So this is the straight away the simulation where the leg is making the proper motion, like a human does or like an animal does. They do a cycloid motion. They put the foot on the ground, move it in a straight pattern, and then they lift the foot and do a cycloid motion, and then again they put the foot on the ground, and like this repeats on and on. So before this, I had different type of motion where there was no cycloid. So when the foot was hitting the ground, it instantly came up and then did some displacement and then instantly hit the ground. So then that is not the realistic motion. So I have improved this code. You can see that you can say that this is the third version of the code. So if I run this simulation after, so everything after this code is regarding the kinematics. So I'll be posting this code in the GitHub page, so you can get it from there. So this is the reverse motion. So this is the femur joint. This is the shank joint. This is the shank joint, the knee, and the femur. Femur and hip are like close together. Hip joint and the femur joint are very close together. So here there's no hip servo, just a 2D displacement of the foot and how the leg moves. So okay, this is a bit a sign convention. So when I do the forward, it makes a reverse. If I do this forward motion, you can see that it makes a straight motion, goes up, does the cycloid motion, and then hits the ground, makes a straight motion, goes up in a cycloid fashion, comes back, and like this repeats. So this is simulation. So this is the stance phase, is where your foot is on the ground, and the swing phase is where you actually make a swing in the air. The foot is making a swing in the air. So yeah. After that, I have a 2D version which is a little bit improved. A little bit improved in the sense that I have this hip servo which is fixed here. The hip bracket. This is the actual. So this is the actual hardware representation of the robot. So you see, the hip servo is connected using a bracket. If I show you this actual diagram. This is the servo, this is the hip bracket. This is length here. The hip joint is here, the femur joint is here, but say this is the hip bracket. Okay, so you can see that this is the forward motion and this is input code. So forward actually moves forward, and it's very slow to let you see how the code works. Okay, the stance phase, now the swing phase, the foot makes swing, then comes back and hits the ground, and then makes a straight motion. So this is what you call stance and swing phase. Okay, if I do the reverse motion, you can see the foot goes in reverse. So this is this direction from the blue line to the this z-axis. This is the y. So when the robot goes to the left, it goes in a forward direction from the reference of this figure. This is a forward motion, and like this one. So this is it, two-dimensional. And if I can imagine, if I can visualize, you can see that this arm, this leg moves in the uh, ZY plane. Okay, from the reference of a robot chassis.